Boa tarde a todos. É uma alegria retomarmos aqui o nosso ciclo de seminários do departamento. Está funcionando? Tá ok. E aí? Ah, entendi. Boa tarde a todos. Boa tarde a todos. Boa tarde. Alô, alô, alô. Assim tá bom? Tá bom assim? Tá bom então. Boa tarde a todos. Então, retomamos aqui o nosso ciclo de seminários. Hoje nós temos a alegria de receber aqui a doutora Camila de Sá Freitas. Ela é fellow do ESO, com atribuições em Paraná, desde dezembro de 2023. Ela fez a graduação e o mestrado em astronomia no Observatório do Valongo, na Universidade Federal do Rio de Janeiro, e o seu doutorado em astrofísica no ESO, na Alemanha. Atualmente, os interesses de pesquisa dela abrangem diversos aspectos da evolução de galáxias, com foco em evolução secular, dinâmica, evolução estrutural e morfológica, e quenching de galáxias. E sua principal linha de pesquisa atual é determinar a época de formação de barras em galáxias próximas e os aspectos evolutivos associados. Muito obrigada. Ela vai fazer o seminário em inglês.
Obrigada. Muito bom estar aqui. Eu acho que é sempre interessante conseguir apresentar o trabalho aqui em institutos do Brasil e conectar mais com a comunidade. Então, é uma alegria para mim poder estar aqui hoje. E, bem, o talk vai ser em inglês, mas no final, se alguém tiver perguntas e não se sentir à vontade em fazer em inglês, pode fazer em português. A gente pode conversar também bem tranquilo, sem essa pressão. Com a introdução, acho que resumiu muito bem qual vai ser o talk de hoje. Tá, eu estou me ouvindo, tá. Então, vamos começar. I'm going to talk a little bit about the timing bar formation epoch in nearby galaxies. This is a project that started in my PhD, and now we kept developing it, and we have some very interesting results. But before getting to the topic, I really want to go back and talk what is a bar, what I'm talking about, because I know some people in the audience are not from extragalactic, and even people that work with galaxies, sometimes they don't really know what is a bar. So a stellar bar, as the name says, is a stellar structure that is very, very present and common in galaxies in the local universe. And this is an axisymmetric structure in the galaxy with a pattern speed rotation. So it rotates like a solid body, okay? So we're talking about a structure that and rotates, and then obviously also affects the galaxy in different ways. And talking a little bit more about bars, I don't know if this will work, because we all know how technology is. Let's see. No, it did not work, but just to exemplify, a lot of people wonder how bars can exist and persist as a structure, since it's a non-axisymmetric structure. And here what we should follow is a video of the same galaxy. On the left, your left, we are following the galaxy rotate, and we can see the bar rotating. And on the right, we are following the galaxy, but we are rotating with the bar. And with this video that I will gladly show later if someone is curious, with this video what we can see is how the stars sustain the bar, especially this one that we call the X1 family bar. Tá tudo bem. É com mouse? Espera. Yay! Thank you. Okay, so what we're following here are the same three stars to exemplify how the bar can be sustained. So when we look at the stars in the middle one that we call the backbone of the bar, we can see on the left panel how they rotate in the disk of the galaxy. So this is how bars exist in the disk galaxy for many, many years. Okay, so now that we all know what bars are, we can start thinking why we care about bars. And this is a motivation that I like to do, because bars are most likely ignored by most people that do galaxy evolution. So why do we care about bars? The first example I like to think is that they are associated with the disk maturing in the universe. So when we think about morphology across redshift, the usual picture is that in the early universe, we have all these galaxies with messy morphology, and they are very influenced by external factors, right? So they are interacting with other galaxies, they are going through mergers, and they have this turbulent morphology. As time passes, in the intermediate redshift, what we expect to find are some disks, but usually they are still very thick and they are very turbulent as well, which shows that they're still going through a lot of interactions with other galaxies. And then in the local universe, we start having these well-defined disks with order motion and so on. Just a note here that how intermediate redshift these turbulent disks are is something that is changing very fast now with James Webb results. We used to think that it's more or less redshift 2, but now with recent results, it looks like it's more like redshift 6, even higher. So this is something that is really under debate right now when this disk material starts to appear in the universe. But when we look at the general picture, it looks like that the galaxy evolution goes from external process to internal evolution. And here I'm talking mostly about these galaxies that are not going through interactions and are not in clusters of galaxies and so on, right? That they don't have a strong influence from their environment. And what is interesting is that soon after the disk matures, this means that the disk has a cold dynamic, it can form a bar. So the formation of the bar, according to theoretical work, will take place shortly after this cold dynamic sets place. So if we know when the bar forms, we can also infer for how long this disk has existed in the universe. So this is the reason number one of why we care about bars. The second one is that the bar will affect the host galaxy in many different ways. I'm going to list some ways here. So the first one is that the bar redistributes material and angular momentum. So the orbit of the stars are altered, you have gas going in and out, you have angular momentum moving outwards as well. So you're causing an internal evolution of the galaxy. The second one is that it can lead to a global quenching. So what happens is that the gas, once the bar forms, it funnels inwards, and then the disk of the galaxy starts to have less gas to form stars. Then in a general way, we see that barred galaxies are more quenched than non-bar galaxies. And we associate this to the bar causing this gas exhausting. And the third reason, a third affection, let's say, is the structure formation. So because of this redistribution of material, we can form structures that were not there before the bar. One of them is in the very center of the galaxy that we call the nuclear disk. And it will be very important for us here, moving on the talk. So these are a couple of ways that the bar can affect the host galaxy evolution, and more than that, can start to lead the internal evolution of this galaxy. Another reason is that more than half of the galaxies in the local universe have bars. So when we look at the bar fraction over time, in the x-axis we have redshift, so the local universe is here on your left. When we look at the bar fraction in these galaxies, we have many studies agreeing that you have more or less 70% of these galaxies with bars. So this is to say that they've been affecting the galaxy and they've been affecting most of the galaxies. So if you care about galaxy evolution, it's often interesting to understand if this galaxy has a bar or not. So just to summarize why we care about bars, like I said, the moment they form, key moment for galaxy evolution, they can affect the host galaxy. More than half of the galaxies in the local universe are affected by the bar. And a fourth one is that many simulations, the most recent ones, they point out that the bars, once they form, they are not easily destroyed. So once they form, and many studies believe they're old structures, they affect the galaxy for a long time. Then the remaining question is, when did these bars form? So when we look in the nearby universe, the 70% of these galaxies with bars, we don't know when they formed, and we don't know which similarities they have or not. And this is where my has been focusing more recently. So, tackling the problem of when these bars formed, we need to understand how to time the bar formation. And one main problem is that if you use stellar population, you're going to have a problem because the stars that compose the bar, they were not formed with the bar. So the bar forms in a dynamical way, and it's composed by stars that were already present in the disk. This means that if we do this telepopulation analysis of the bar region and so on, this will not correspond to the dynamical formation of the bar. And this is why this has been such a difficult question to answer in the local universe observationally. What we can do instead is to use bar-built structures. So more specifically here, I'm going to be using the nuclear disk, which is the central structure. And and this is because we know that from simulations that the nuclear disk will form shortly after the bar formation. So if you do manage to detect the oldest stars that belong to the nuclear disk, these stars have the same age of the bar formation itself. So that's the idea here. Then, of course, there is a catch, and the catch is that the nuclear disk formed in a region that already had stars. And then you need to be able to separate which stars belong to the nuclear disk and which stars were already there before the nuclear disk formed. And this is a methodology we presented in my paper in 2023 for a pilot study. So in a nutshell, because I think I don't want to bore you with all the details of this methodology, how did we do that? Well, we have the nuclear disk, and then we have the star formation history from this region of the nuclear disk. This is the star formation history of the whole data, so let's call it the observed star formation history. Then what we do is we use the region around the nuclear disk as a representative star formation history. So what we're assuming here is this region around the nuclear disk has the same star formation history of the, let's say, the stars below the nuclear disk. And this representative star formation history is enough to clean the observed star formation history and leave us with the star formation history of the nuclear disk. So this was a bit fast. Feel free to ask me more questions. But the general idea is to take the observed star formation history and remove everything that was not there before the nuclear disk. That's what we want. Then, of course, this is a new approach. We were not sure if this approach was valid, let's say. And what we did, we tested it in simulated galaxies. And one interesting thing we found is that, okay, the star formation history that we derive for the nuclear disk is not completely clean, but we found a good proxy of the moment of the bar formation. This proxy is when we use the ratio between the blue and the green one, so the nuclear disk and the main disk. We use this ratio, and this ratio is above 1 for the first time. This is usually related to the moment of the bar formation. So this is what we did. Again, it's in a nutshell. We've done many tests, and we tried to assess the systematics in many different ways. And this is how we moved on with the methodology for observed galaxies. So the first time we applied this was for a pilot study, so NGC 1433. And this is how the real result looks like. So on the top, I'm giving you the color code so we can remember. But basically, what we are interested in is the bottom panel and the time that this crosses 1 for the first time. We did this for the first time for NGC 1433 into 2023. And the interesting aspect of this methodology is that it is broadly applicable. For the first time, we have a methodology that doesn't depend on specific characteristics of the galaxy. If you have IFU and if you have a detectable disk, in principle, you could apply this methodology as well. So that's how powerful it is. A little parenthesis here to talk about the Milky Way. This was the second time we applied our methodology, not for the Milky Way, but to contextualize the Milky Way. The Milky Way does have a bar as well. And the interesting thing is that the age of the Milky Way bar is more or less 8 to 9 gigayears, depending on your depending on different studies. I've seen 3 to 4 and also 8 to 9, but I'm not gonna address which is the age of the Milky Way bar here. But the interesting thing is that the nuclear stellar disk in the Milky Way is very small. And then the communities between the Milky Way and the extragalactic bars, we were always wondering if this is a resolution problem or just because we define things in different ways and maybe we can't compare them directly. So in the second paper of 23, what we did is that we found two nuclear disks that are also very small. And these are in the galaxy NGC 1566 and NGC 289. These nuclear disks have less than 100 parsec, and the Milky Way nuclear disk has around 120 of radius as well. So in sizes, they are very similar. But for these two galaxies, we find the bar ages to be very young. So one is more or less 1 gigayear, and the second one is 4.5 gigayears. So when we contextualize the Milky Way, here the Milky Way is a star, it looks like the nuclear disk size is very similar, but maybe the age is not that similar. And maybe we could start to be painting a picture here of how the nuclear disk grows. Maybe it grows in exponential. This is just to contextualize a bit how this relates to the Milky Way as well, and how this have been moving forward from an extragalactic perspective. So moving forward, we have a methodology that we can apply to many galaxies. So now what we want to do is apply them to many galaxies. And the perfect sample to do this is the timer sample. Not by coincidence, because the timer sample was built with that purpose, so it's tailored to answer this question. The timer sample is 20 galaxies, and we have MUSE observation of the very center part of these galaxies. So what we did, we applied the same methodology for, and we have individual results for all of them. Today I don't want to focus on these galaxies individually. What I want to focus on is what we can learn from them as a group. So which evolutionary aspects we can investigate now that we have 20 galaxies bar ages, which is the largest sample. So the first obvious question is, how old are bars? When we're looking into the nearby galaxies that have bars, what can we expect? And well, surprising or not, we have bars from all the ages. We have very young bars with 1, 2 gigayears, but we also have bars with 12, 13 gigayears of age. So this is telling us, as expected, that this process started very early, which is in agreement with the recent results with James Webb, for example. But you still have you still have galaxies forming bars more recently in the universe. So this is an ongoing process. Taking a step further, I separate this sample according to the star formation rate in the nuclear disk. And this is what we're looking at now. So in purple, I have nuclear disks with high star formation rate density. In yellow, I have star formation with low star formation rate density. And it's very clear when we look in the top especially, that nuclear disks hosted young bars still have a high star formation rate. And all of this makes sense because at some point, as the bar keeps funneling gas inwards, at some point you're not going to have as much gas anymore, and then the nuclear disk will start to quench as well. So this is a second result we have. And taking a step further, we can connect the bar ages with the studies with high redshift. So the idea is that we use telescopes to find bar fractions further and further away. With James Webb, I think the record now is redshift 4. But from this perspective, what we can do is look at the bar ages and then infer their bar fraction. So that's what we're going to do now. To do this, what I did was to build a cumulative distribution of my bar ages. And then, of course, what I have for my sample in the local universe is a fraction of 100%, which is not correct. But that makes sense because my sample, all my galaxies do have bars. So what we did was to normalize the last point to the observed bar fraction of 67%, and this is how it looks like. Then, of course, we want to compare with observed bar fractions, and this is what we find. So the black dots, they have different shapes because they're coming from many different studies, and it's very impressive that they all match very well together, including the new bar fractions coming from James Webb results, which are these last points here. So this is a new approach to extrapolate the bar fraction over time. And even more interesting is that our sample is not volume limited yet. It would be great to have it volume limited and then repeat this exercise to see what we can find or not. So these are some of the first results we have from this methodology. But then we can also look for the first time some evolutionary aspects according to bar aging. And these results from now on, they are even feel a bit disconnected with each other, just because we're addressing many different aspects of galaxy evolution according to bar age. Okay, the first one is the role of downsizing. So in the perspective of downsizing, what one might expect is that the most massive galaxies today, they were the first galaxies to assemble their mass. This is what we understand with downsizing. If they were the first galaxies to assemble their mass, one might expect that they were the first one to have enough mass to form a bar. So with this perspective, we would expect that the oldest bars to be hosted by the most massive galaxies. That was the idea. But when we look into it, we actually don't see any correlation at all. So when we look at the stellar mass with bar aging, it's really flat. We thought maybe this could be related to catalogs, so we tried 3 different catalogs, and all of that show no correlation. So this looks like that downsizing doesn't seem to be the constraining factor to form a bar or not. Let's put it this way. So mass is necessary, but might not be enough to be able to form a bar. This is the first result in a general aspect. A second one is related to bar-related quenching. So in the scenario of bar-related quenching, we have 2 possibilities. One is that the galaxy forms the bar and then quenches. So the bar is responsible for quenching that galaxy. And the second one would be that a galaxy that is already quenched will form the bar, because a galaxy that is already quenched has less gas and is more likely that it will form the bar. So these are the 2 possible scenarios, and we wanted to look into a little bit. One way to look into that is in the panel of the specific star formation rate with mass. In this kind of phase space, we usually define a main sequence here in black. And I'm showing also, so these values are from 2019, so it's completely unrelated to our methodology. And in the background, in the density map, you can see the whole Leroy sample here. And I'm showing my galaxies in this context as well. And what is common to define from this phase space is the main sequence offset. So basically how from the main sequence your galaxy is. If you're above it, you're bursting of star formation, and if you're below, usually you're quenching. And then when we plot the main sequence offset with bar age, we find a very tight correlation showing that the oldest bars are more quenched and the youngest actually they're bursting, which is not completely surprising because most of the star formation is happening in the nuclear disk itself. This doesn't reply the question if the bar is causing the quench or not, but it's very reassuring to see that the quenching is related to the bar in a way, because we have this very tight correlation. Then looking further, we wanted to understand if these galaxies are quenching because they don't have gas, because the bar is exhausting the gas, or because of something else. So what we find when we look into the content of hydrogen 1 is that you don't see a correlation that tight anymore. You see a weak trend. So it can be because you're using more gas, but this is not enough to explain. And in some way, you can be affecting the star formation efficiency as well in these galaxies. And this is something to be further investigated, which we didn't do yet. But back to the question of mass assembly and the bar-related quenching, we have 5 galaxies in our sample that we have IFU data for the entire galaxy. So we can investigate the star formation history of the galaxy as a whole. And this is what I'm showing here for these 5 galaxies. We have most galaxies, and then we can construct in general how this galaxy evolved so far. And from this star formation history, what we can do is understand how these galaxies assemble their mass. So this is what I'm showing here. In the leftmost panel, we can see the cumulative mass assembly normalized to 1. So we can compare them 1 to 1. In the middle one is the total cumulative mass over time. And in the right one, we have how the specific star formation rate changed over time. And in the 3 panels, I'm showing you the moment that the bar formed. So we don't want to, of course, overinterpret our results because we only have 5 galaxies, but we start to have some interesting aspects that we can already see. Going back to the downsizing, what I said is that the present day mass doesn't relate to the bar age. And in the middle plot, this becomes even more clear. So when we see these two galaxies, they have very similar present day masses, almost the same. But they assemble their masses in very different ways. How fast they assemble their mass was very different. And not coincidentally, the moment of their bar formation is also different. So the present day mass is not a good enough indicative of the downsizing in this context, because these galaxies, they assemble their mass in different ways. Another interesting thing to see is the specific star formation rate. All of them form the bar after, let's say, maybe an upper limit. And this also makes sense because we have from simulations that if your galaxy is forming too much stars, if you have too much gas and you're bursting in star formation, you're not going to manage to form a bar. So maybe this is the first upper limit that we can determine in an observational way. And taking a step even further, we can investigate quenching. Like I said, the space phase of specific star formation rate for stellar mass is very good to understand quenching. The general picture we have is usually a main sequence. The galaxy will build up its mass from left to right, so from lower masses to upper masses, of course. At some point, this galaxy might quench and move downwards in this space phase, not building up much more mass, and then we'll be in a cloud of quenched galaxies. So this is the general idea of it. And if we look at our galaxies, this is how they look in this panel as well. So, which is very interesting, is that 4 of the 5 galaxies, they have the bar formation right before a drop in the specific star formation rate, which could be an indicative that for these galaxies, the bar formed and then the galaxy quenched. And then the 5th one, which is NGC 1566, it looks like this galaxy formed the bar after quenching, so after consuming most of its gas. And this relates to the normalized cumulative mass, because when we look at the plot on the left now, we have the oldest bar in a galaxy that assembled its mass faster, and the youngest one in a galaxy that assembled the mass slower. So this is related because this is the normalized mass for the present day. So the idea is that the galaxy with the oldest bar assembled its mass faster because when it formed the bar, it quenched. So the mass itself didn't evolve that much ever since. So that's how these things relate. This is a work in progress, but it's the first time that we can diagnose in the galaxies what happened first, if it was the bar formation or the quenching of the galaxy. And well, hopefully we're going to manage to do it for a much larger sample in the future. One last thing, sorry, too much information. One last thing is the insights we can have now on structure evolution. So like I said, the bar is responsible for forming structures, and these structures will also evolve with time. The bar itself, when we look at the normalized bar length with bar age, we find that the oldest bars are larger than the youngest ones. This can be either because the oldest bars form larger because of different aspects, or it can also be that they grow with time. This is under debate as well. A second aspect is how strong this bar becomes over time. So the idea is that this bar, as time passes, will continue capturing stars, becoming larger and becoming stronger, which means harder to destroy. And we see that the strength in y-axis here is the 8. It also seems to increase with time as the bars grow older, which is expected. And a third one is how the nuclear disk size evolves with time. And again, we can find that the oldest nuclear disks, they are hosted by the largest nuclear disks are hosted by the oldest bars. And here we have an even more interesting aspect when it comes to the nuclear disk, because we also look into how the nuclear disk assembles its mass. So what I'm showing in the left plot is a summary of how nuclear disks evolve. We can see that the young ones, the ones hosted by young bars, they have a relatively stellar mass, which is expected because they're still building their stellar mass, and it's color-coded for the star formation rate. So the young ones are the ones that have a very strong star formation rate. But then as time passes and the nuclear stellar disk also is assembling its mass, so it's also growing in mass, they also start to quench either because they don't have more gas available or because the star formation is not as efficient anymore. Okay, so this was a lot. I'm going to leave you with some takeaway messages. The first one is that we developed the first broadly applicable methodology to time the bar formation in nearby galaxies. The second is that the bar formation seems to be an ongoing process that first took place in a long time ago in the early universe. We are proposing an independent way of estimating the bar fraction over time. We find a very clear correlation between the bar aging and the galaxy quenching, and now we even have a step further of evidence that the bar is of these galaxies. When it comes to downsizing, the mass, present-day mass, is not good indicative of how long ago the bar formed, especially because we can see now that these galaxies, they assembled the mass in very different ways. And the last one is that the structure evolution itself, we can investigate how they evolved from a traditional perspective from the first time. Thank you so much for your attention. I'm taking any questions now. Thank you.
Thank you, Camila. Very nice talk. Questions?
Thank you for your talk, Camila. Very interesting, very informative. Your method is based in the comparison of the stellar populations, the nuclear ring, and in the bar. And what about stellar migration? Because they will pollute, I would say, exactly the region where you are applying your methods.
Well, that's a good point. And the bar will be responsible for a lot of the stellar migration as well. In our attempt, what we're trying to look is the oldest stars that belong to the nuclear disk. And we do this by removing the stellar population outside. So let's say you have stellar migration. It's not clear how much of the mass these stars migrating will affect the region. You see what I mean? So how much they will pollute my estimative. And then another thing is that we expect them to be not only in the nuclear disk, but also in the region that we are using as representative. So in principle, I would say that we might be removing them and they probably will not affect the method that much, but it would be very interesting to actually test that. So in simulated galaxies to understand how this migration can affect our methodology or not. It's something we didn't manage to test so far. Thank you.
Hi.
Hello.
Thanks for your talk. I have a curiosity. Have you checked if bars in isolated galaxies have the same characteristics of those in galaxies belonging to clusters? I mean, is there some environmental constraint in bar formation and evolution?
I did not check it myself. I know there are studies that do check those. But yes, there are environmental constraints in the sense that for a galaxy to be able to form a bar, the galaxy needs to have enough mass that interactions with nearby galaxies will not be a huge problem, let's say. And then we see from simulations that if you have a disk galaxy with a certain mass and you had minor merger, it's not a problem. But then if you have 2 consecutive minor mergers, then it's harder to form a bar. So having too many interactions, because the role of the interaction is a bit under debate, because the interaction can either trigger the bar formation or destroy a bar that is about to form. So the idea is that having too many interactions probably will prevent your galaxy from forming a bar. What I find interesting to think is you do have clusters, galaxies in clusters that have bars. So what I find interesting to try to understand if these bars formed before or after entering the cluster, which is something we don't know yet. Thank you.
Following up with that, actually, just a comment, the strange galaxy, the NGC 1566, actually is part of a group of galaxies.
Yeah, a group.
So maybe there's something there that the quenching maybe happened before the bar fully formed because of this galaxy interaction. Maybe.
Yeah. No, that's
it could be a good possibility for that.
Yeah, and I'm not completely sure, but it looks like maybe 1566 went through a minor merger recently. Not completely sure that either. But that's a very good point. Thank you.
Camila, very nice talk. Thank you. I was wondering if your technique could also be used for galaxies in general, not just bar galaxies. Like the technique, if you want to compare any two adjacent regions of a galaxy, would this work also, or there's something special about bars because of whatever that this works better here?
Well, I think there are two steps here. The first step is structures that coexist. In principle, we could try to disentangle their star formation history. Although we know, for example, for the nuclear disk itself, you don't completely clean the star formation history. This, I think, can be, in principle, can be reproduced in other regions of the galaxies. Now, the proxy for bar formation of being above 1, this is something I think it's more specific.
Yes, that's true. No, I was talking about the first part. I think that could be interesting. You mentioned this example of when you have two structures in the same spatial region. Can you think of any other situations where you could use your technique? Because it's a very nice technique, and I don't know if it have been used before. I have never seen this subtraction of star formation histories. It would be nice to see in your paper probably how you do this in detail. But this seems a very powerful tool that maybe can be used more broadly. Yes.
So I can't take full credit of it because I actually saw a talk on nuclear stellar clusters. And they do something similar.
I see.
It's much simpler because the nuclear stellar cluster are non-resolved sources, so it's easier to make this this clean. Let's say it's more similar, let's say, to exoplanet atmosphere that the planet is not resolved, right? So I know they're used for nuclear stellar clusters, not to determine the moment of formation of the nuclear stellar cluster, but to try to isolate the star formation history of the nuclear stellar cluster.
Yes.
Yeah,
that's what I thought. Is just to isolate some structure and just find the star formation history of that structure, of that. I have another question. Your sample.
Just to follow up, I think this can also be applied to globular clusters in general and other structures. For example, the bar forms other rings. So I think it would be interesting to see in those as well. But
I do not understand how you would use it for globular clusters to find out what.
Maybe how old the globular clusters are. Globular clusters that are co-spatial with the disks, for example.
I see.
People are doing this.
Yes, I understand. Okay, good. My second question, sorry, very quickly. Your sample seems to be a bit small, like galaxies have bars everywhere. Why do you have this size of sample?
Well, because getting time on MUSE is very hard.
Sorry?
So
because
getting MUSE time is very
MUSE,
hard.
yes.
So the timer was proposed in 2015, and they targeted 20 galaxies with more permanent central structures, because also nuclear disks were not, let's say, fully understood at this time as well, because at the point we were studying these structures mostly from the photometric perspective. So timer was proposed 10 years ago, already with this goal, but nuclear disks themselves, they were not fully understood. So they couldn't ask for a lot of time, let's say.
Okay, I see, I understand. No, I had not understood this a specific project, but I thought you had just looked more in the database of MUSE, for example. Because there are so many cubes now in the database of MUSE. I would think that there would be more bar galaxies there, but specifically of this this database that you had specific for timer. Okay, thank you.
I am following up on a different project on central structures that I checked the MUSE archive, let's say. Then we find many other nuclear stellar clusters, and in the future would like to also apply this for these galaxies as well. But so far we focused on timer because this was a timer achievement, let's say, and we wanted to focus on the sample first. Thank you.
Hi, Camila. I have a question. Can you go back to that slide where you have the Milky Way?
Yes, I knew you were going to ask about the Milky Way. Yeah.
And not this one. The one that was the nuclear disks versus
this one. Yeah.
This one. So that Milky Way point there came from where?
I think it was Sanders.
Okay.
Yeah.
So, yeah, so I think the Milky Way is still the pedra no sapato.
Yes.
The stone in the, como se fala? Yeah, because it's difficult, right? And what we did for the Milky Way, independent of looking to this, and I think I quote even one of your papers showing that there are bars that are younger.
Yeah.
Because in the beginning, everybody was thinking all bars have to be old.
Yeah.
So there are bars that are younger. If your method is correct, you show that there are some bars that are younger, right? So in the age of the bar that we determined from stellar, in the Milky Way, stellar populations that are, it's a very complex way to explain this, but stars that are today here nearby, that are supermetal rich, that have come from inside, they kind of date for me when there was this moment of bar formation. Yeah. I got a value of around 3.
Yeah.
3 gigayears. So
I know the paper. Yeah, I met the first author.
Okay, my PhD student.
Yeah.
So that star would be exactly there, but it would be exactly there. Yeah.
Yeah, I know.
So, and everything I've heard so far about age of the bar is based on simulation, except from our data point.
You mean age of the Milky Way?
It's age of the Milky Way. There is the Sanders work.
Yeah, there's also the Kawata one, no?
Yeah, it's the same group, right? They are using Mars, right? But if you look to the paper, if I understood correctly, it's again also linked to simulations, right? Okay. So in this sense, I think there is right now a discrepancy that would be interesting to check. Yeah. Essentially, we do not find this. Okay, so that links to the question I want to have to you. In the simulations and in the other galaxies, the bar age is the bar you see now, but this bar could have formed, to be destroyed and reform. So I don't know exactly. So what we are saying is that the last time the bar in the Milky Way formed was 3 to 4 gigayears ago. Yeah. But is not against the fact that 10 gigayears ago there was another bar.
Yeah. Yeah.
So do you see this in the simulations, that this come and go?
Okay, I have a couple of points. I know I study from the group in Granada on the nuclear stellar disk star formation history. Have you seen their work? Okay, so it's the nuclear stellar disk, and they derive the star formation history of stars that belong to the nuclear stellar disk. It's much easier because then you can do the selection kinematically of star by star, right? And they see in the star formation history of the nuclear stellar disk a peak 8 gigayears ago, then nothing, and then a second peak, I think 4 gigayears ago. So this makes sense with what you're saying. I can send you the authors later. So this makes sense with what you're saying. And then linking to simulations, what they find is that usually when the bar forms after redshift 2, they are forming in galaxies that have enough mass to sustain them. So they are not usually destroyed. To destroy them, you would really need a major merger and then have a whole morphological transformation. The bars before redshift 2, sometimes they are formed in galaxies that don't have enough mass, and then they are more easily destroyed. This is what the most recent simulations are finding about bar destruction. And then back to what we find, like you said, is the latest bar formation. So is what we're expecting to be the current bar age, let's say. But we don't discard the possibility of some of these bars being a second generation bar. But this is something that right now I don't know how to investigate in this sample we have. Does that make sense? Okay, nice. Thank you.
More questions?
Yes, I do have one.
Okay.
Thanks, Camila. Nice talk. I was wondering if you have looked into the correlations with the bulge of the galaxies to see if you have a similar correlation between the galaxies that have a larger bulge with the quenching that you see correlated with the bar.
Okay, so the whole bulge topic, I think it depends where you're coming from. If you're coming from photometric studies or kinematic studies. I'm gonna assume photometric studies. Is that right?
Yeah, could be.
I'm sorry, I'm making this distinguish because what we've seen from photometric studies that, well, we find bulges or whatever we're calling bulges, right? But then when you go to the kinematic perspective of it, we don't find any indication of having a dispersion dominant structure in the center. So this to answer that in these galaxies, we don't see any evidence of actually existing a bulge. And a lot of studies are finding now that what we were calling bulges, or the classical perspective of it over dispersion dominant bulge and so on, often are related either to the nuclear disk that is not resolved or structures related to the bar itself that is not resolved. So this to answer that, I didn't look into that, but because the whole evidence of the existence of these bulges is not that clear from a kinematic perspective. Does that make sense?
Okay. No, it's just because some of mechanisms, secular mechanisms responsible for quenching galaxies are the formation of the bulge. That's why I was wondering if you have checked on this, but I understood your point. Thanks.
Yeah, because a lot of times this formation of the bulge, they are referring to the bar, or even there's a structure associated to the bar that is the box peanut bulge, and then it's not the classical idea of a dispersion dominant bulge, right? So that's why there is some, let's say, some debate on what is a bulge. I think in the latest conferences I've been, every time someone says bulge, someone will ask, what are you calling bulge? Because there's been a lot of debate of what is a bulge, basically.
Yes, thanks. I understood. Thanks.
Thank you.
Hey Camila, very nice talk. Thank you. I'm still wrapping my mind around the disconnection between the bar and the nuclear disk, because what you measure is the nuclear disk, and then you assume that the bar is related to that. So, but I was wondering, in cases where the galaxy hosts bars that are purely stellar, if that exists. So I'm just imagining that case. So I have no gas. So in that case, I would not form a nuclear disk. So I wonder, is that a possibility if those galaxies exist? And if so, in that case, you cannot date the bar because you don't have the nuclear disk, if I understood correctly.
Yeah. So you're saying that if the galaxy is purely stellar, yeah. What I've seen in most recent simulations, there was a very nice work like last year from the FANGS collaboration that they find that above a certain stellar mass, usually 10 to the 10, galaxies, even with very small fractions of gas, they form the nuclear star disk. I think I don't remember the lowest gas fractions they used, but that's what they found. Below 10 to the 10, then it's a bit of a different story, because then, well, it's related to other perspectives of the galaxy. And then you would really need a galaxy to have no gas at all to form a bar and not form a nuclear stellar disk. If that's the case, you're absolutely right. Because then if you have a galaxy with no gas that forms a bar, you're not going to have the nuclear stellar disk, and we will not manage to do what we do. But what we're finding from simulations is that this is not likely.
Okay. So if they exist, they are rare in any case.
Yeah, if they exist, they should be rare.
It's not something expected to not have any gas that will not form at all the nuclear disk.
I think no.
Okay.
I think in disk galaxies, I think this is not expected. That was my takeaway from that work.
Thank you.
Thank you.
More questions? Okay.
Why some galaxies have bars and the others not?
That's also my curiosity. No, there are a couple of processes that could prevent a galaxy from forming a bar. And when we see from a simulation perspective, we find that it's very easy to form a bar. So we started to have to explain exactly why some galaxies don't have a bar. There are some explanations. If you have, for example, too much star formation in the disk of the galaxy, I don't remember exactly the connection, but if you have a lot of star formation, you don't form the bar. If your disk of the galaxy is not cold enough, you're not going to form the bar. And if you have a central structure that is very massive, which people argue that is not feasible, but anyway, if you have a central structure that is very massive, and also properties of the dark matter halo can also affect. These are some of the reasons, but no one will know how to tell you why some galaxies don't have a bar. Not yet.
Okay. Okay, the last one.
We know that we have galaxies with several bars inside of bars.
Yeah.
And then in this case, how is possible to estimate the age of this?
Yeah. We know that, that's true. What I've seen in this topic so far is that the second bar is usually hosted by the nuclear disk itself. And then the latest results I've seen is that we expect the second bar to be part of the nuclear disk history. So the idea is literally galaxies inside galaxies here. And what we do, we have, I think, 4 galaxies with the nuclear stellar disk with an inner bar. We keep them because we understand that the star formation history of the stars of that bar are also related to the nuclear disk star formation history. So we kept them. And what we found is that these systems, it's 4. These 4 systems, they are the oldest, they have the oldest bars. So what we understood in the formation scenario of these second bars, there were some possibility of formation scenarios, and what we find is that they are in old systems. So you need to first form the main bar, form the nuclear disk, quench the nuclear disk to be able to form the second bar. This is very speculative at the moment, but usually the second one is inside the nuclear disk. Yeah. Thank you.
Okay, thank you again, Camila.
Thank you very much. Thank you. Obrigada.